Okay, here we go. So today we're talking about, we need to get into the quantum mechanical model and electron configuration. So from now on, everything that we do in here is going to be brand new to you. You've probably never heard of this stuff before, even on like a video or movie or TV show. This stuff is like, there's a lot of brand new stuff moving forward, okay? Some of the class you've heard of before, in this unit, and specifically this lesson, it's all new. Nothing's you've probably heard before in your life, okay? So that's why you really got to pay attention, and if you feel yourself dozing off, stand up. What's that? That's for you. Oh, I got to start yours. Okay. Is it up? So, to review the Bohr model, the Bohr model obviously kind of looks like this, and you learned it in 8th grade. We talked about it already this year. We have the nucleus in the middle, we have electrons around that nucleus on rings, and the very outermost energy level where those valence electrons are found, those are called valence electrons. That's all review for you, okay? There's something called the octet rule. The octet rule is where we have the outermost energy level full of 8, right? But there's an exception to that rule, right? What's the main exception to that rule? Helium, right? Helium's still happy. It's in that noble gas family, but it only has 2 because that innermost energy level can only hold up to 2. And it's full. And later on in chemistry, you'll find out that actually in 4, 5, 6, and 7, can hold more valence electrons, but only really 8 of them are involved in the reactions. Okay? And that's kind of where that octet rule comes from. All right? Only 8 of them are involved in reactions. Okay? If they have that full 8, we say that they are exceptionally stable or they're non-reactive. Same thing. Okay? That's what that term down there says. They're non-reactive. Okay? And that's our noble gases. So the Bohr model of atom is not the best one we can use anymore. Right? We learned that last unit with the history of the atom that the Bohr model isn't the best. There's a better one because of our increasing knowledge of what electrons do and what they don't do. Okay? Electrons move around the nucleus, that's okay, but how they move is where it gets to be different and not right from the Bohr model. Okay? So these guys, these are just scientists. You don't really need to know much of them. They did a lot of mostly math, some experiments. Bohr you've heard of. He did some more work with his own model that they found that actually electrons specifically act as particles and as waves at the exact same time. That doesn't mean much to you right now, and this is where physics really overlaps into chemistry and back and forth particle physics. You ever heard of that term before? You watch Big Bang Theory, I'm sure you've heard it. It's kind of an old show. That's where physics really overlap into chemistry, and physics are the basis of everything, okay, because of how these particles act in chemistry, okay? But this is your first term. So if you were to make vocab cards for Unit 3, this will be your first vocab card. What is wave-particle duality, right? This is what I just talked about, how electrons act as particles and as waves at the exact same time. All right? It depends on what experiment they're being put through or what they're doing, of what they'll act more like. But because nothing really else acts as particles and as waves. Either it's matter or it's energy, right? And electrons kind of do both. And that's why they're so hard to predict. Okay? So, because we're discovering this, we had to come up with a new model and not the Bohr model. Because the Bohr model acts like they're on this trajectory that's very predictable. It acts like wave or particles that's always there, stuff like that, and that's not true. That's what we've proven, not we, but these scientists have proven to not be true. Okay, so the Heisenberg uncertainty principle is your second vocab card. That if you're studying, that you need to know. This was a scientist. Heisenberg was a scientist, and he came up with this principle that said that we cannot know the velocity and the position of an electron at any one time. Okay? We don't know, we can't pinpoint where it is at any certain time. We know about where it should be, And that's about as best as we can do because it acts as a particle and as a wave. Okay? And that's what I just told you in this slide. All right? We don't know where they are. We know where they should be, and we can predict with almost certainty where they are, but not all the time. All right? So this video kind of reiterates what I was just talking about. It's only about 15 seconds.
One of the weirdest things about electrons is that we can't exactly say where they are. It's not that we don't have the equipment, it's that this uncertainty is part of our model of the electron. So we can't pinpoint them. Fine. But we can say there's a certain probability of finding an electron in a given space around the nucleus. And that means that we can ask the following question. If we drew a shape around the nucleus such that we would be 95% sure of finding a given electron within that shape, what would it look like? Here are a few of these shapes. Chemists call them orbitals, and what each one looks like depends on, among other things, how much energy it has.
Okay, so once again, this is what we're getting into instead of drawing those rings around the nucleus. Instead of rings, we're drawing shapes. And those shapes are called orbitals. So instead of an electron following a 2D path, think of a tennis ball around this little golf ball, and within that space between the tennis ball and golf ball is the area in which that electron is freely traveling and moving. It's not really going to be outside of that most of the time, and it's not going to be, well, what we can't say is it's going to be there, it's going to be there, it's going to be there. We just say it's somewhere within that shape, right? And then the next energy level, it's going to be somewhere within these shapes. We don't know where, but somewhere, right? Because we can't pinpoint exactly where it is. But we can say it's probably going to be within that shape, all right? That's where we had to come up, where they came up with a quantum mechanical model. All right? Or you've heard it called the electron cloud. All right? Where does that cloud term come from? If you start to look at all these shapes put together, that's where that cloud shape term starts to come from. Because of all these shapes, they don't really overlap, but they look like it when it's in 2D, and there's no definite shape, overall shape look to it. So we're no longer using the Bohr model because of how it doesn't really do the electrons justice. Now we're going to the quantum mechanical model because instead of a 2D, it's 3D, and it shows that the electrons move freely within these shapes. Okay? So the orbitals are dimensions around the nucleus where electrons are found 95% of the time. And you're thinking, well, if they're 95, where are they the other 5%? We don't know. Somewhere in the universe. All right? And once again, these are called atomic orbitals. I'll call them shapes a lot today, but after today I'll start to get away from shape and say orbitals. But you've heard the word shape and orbital, they're the same thing. And this is their probable location, where they're most likely to be. All right, so here's where we start to get to really the background of what we're going to get to at the end. Principal energy levels are an atom's major energy levels, like this. We've learned about this. The outermost energy level is valence electrons, and we've heard about the energy levels. All right? Those are the major energy levels. There are 7 of them. If you look over in the periodic table, you're going to see it. 7 down the left side. 7 periods. Those are major energy levels. Now, today we're learning about the 4 sub-levels. These are sub-levels. Okay, so each one of those levels are going to be broken into sub-levels. Those sub-levels we call S, P, D, and F. You don't need to know what the S stands for or what the P stands for, anything like that, but that's what we call them, S, P, D, and F. Each sub-level is where the shapes are found, the shapes and orbitals that we just talked about. Okay, each shape has a different amount of, each orbital has a different amount of shapes that it can hold. Okay, and within those shapes are where we're going to find the electrons. Okay, And they always fill up in order from S to P to D and F. So the major concept today is about energy, right? It's a lot less energy to stay close to the nucleus and stay there than it is to hold on to electrons that are further away from the nucleus, okay? So your S sublevel, this is where we're going to get started. Your S sublevel has one shape that it has. One shape. Well, every shape from now on, every orbital from now on can hold up to a maximum of 2 electrons. So if I ask you the question of how many total electrons can be found in the S sublevel, the math is one orbital or one shape up to 2 electrons max. So it can have a maximum of only 2. Does that make sense? 2. Here is that S orbital in 3D, right? It's not a circle. Think of like a tennis ball or sphere, because it's 3D. The Bohr model was 2D. That's bad. Your cloud model, quantum mechanical model, is now 3D, and that's what this is obviously attempting to show you. Okay, your P level has 3 orbitals in it, 3 shapes in it. Once again, any sublevel, any orbital can only have up to 2 electrons. Any more than that, and it's full. So 3 times 2, your P sublevel can hold up to how many total? 3 times 2, that's where that math comes from, 6. 3 shapes, 2 electrons per, 3 times 2, up to 6. And then here are all 3 of those P level shapes. All right, side to side, up and down, and then this one's supposed to be front to back because it's 3D. Okay? Then you're the D level. The D level has 5 orbitals, or 5 shapes.
Just the exam, right?
Mm-hmm.
Okay. So there's a pretest.
Just do the exam. That's where the 10 comes from. 5 shapes, 2 electrons per, 5 times 2 is 10. All right, and then here are all the D shapes, and now's the time I can tell you that you don't need to remember the shapes. Right? You won't need to remember that that's a B level shape. That's not what we're trying to do. Okay? But what you will need to know is that there's a D level, there's 5 shapes on it, 2 per, a total of up to 10 electrons total. All right? And then the last one, F level. F level, where most of your energy, takes a lot of energy to keep these things around. 7 times 7 shapes, 2 per, 14 total. All right, so a common theme there, common math through each level. And there's all 7 shapes. So this table, go ahead and try to fill it out how you believe it should be filled out with you and your group. And just a review of what we just did. Look at people around your group if you're not sure what to do. And then you can look up here. There's how many shapes per level? 1, 3, 5, 7. This is just what we took notes over. 2 per, so where did all these numbers come from? Right? 1 times 2 because a maximum of 2 electrons per shape. If you multiply each one of these numbers by 2, that's how you got that column numbers. Once again, y'all are thinking like, why in the world are we doing this? How's this getting? What are we doing? It's coming, I promise. All right, this chart. So what we're doing here is saying This is, if I just have my S level, what's my max number of electrons? So what are you going to put there? It's not a trick question. 2, right? This next one, it's saying, well, what happens if we add levels together? So if I have my max of S and my max of P, how many total electrons will I have? See that? Once again, not trick questions. Same thing with down here. If I add my S, my P, the D, and the D together, how many total electrons are you going to have? That's what you're doing for the next 2. And you can check your answer up here when you're done. Which one? You don't have, I mean, if you want to. So, these are your notes. Whatever, when you go back and look at them, you know what you wrote down. Note those numbers. Okay? So, we've talked about the quantum mechanical model and how that's the best model that we have so far because it shows the nucleus, and now we're trying to better represent the electrons. That's why we use quantum mechanical model. Our next part is trying to figure out how do I write electron configurations. All right? And so you've never done this before. And once again, the big overall theme today is the low energy levels require and are more stable than your high energy levels. And so we're going to fill up your lowest energy levels first before you get the higher ones. And what this is saying is, guys, when you all drew a Bohr model, did you fill in the outer rings first or the inner rings first? If you're doing it right, you fill the inner rings first, right? That's what this is all talking about. Those inner rings, even though they're not rings anymore, the inner orbitals take less energy than the ones on the outside. So you fill those in before you get to the outside. All right? The lower they are, or if everything's in its ground state and nothing is just normal, we call it ground state. Each electron occupies the lowest energy orbital available. This is Aufbau's principle. The next vocab card that I would make for this shooting. Right? Because we have Heisenberg's principle and then wave-particle duality. Hopefully you remember what those two things are. If not, you should make a vocab card. Right? The Aufbau principle is just saying what I just told you. Why did you fill in the inner rings first? Because of this. The lowest energy level orbitals are filled before the higher ones. Makes complete sense, right? Like, you go up the stairs one step at a time, for the most part. Yes? You don't jump 10 at a time because it takes so much energy to do that. You just need to put a name to it. Everybody got that? You need to put a name to it. Right? And then, once again, all your elements up here are in their ground state. Okay? All your elements up there are in their ground state. So, get your periodic table out, the blank one, and your colors out. If it's an emergency, we're about to color the thing. So this would be a great time to stand up and color this thing at a lab table if you're falling asleep, or if you just need to stretch. It's up to you. Okay, so a couple things about the periodic table that you should notice. First off, how many different blocks do you see up here on your table? Well, what else did we talk about that there were 4 of today? The sublevels, right? So guess what each one of these are going to represent? A sublevel. What other major thing is different about this periodic table, other than it's broken apart into blocks, that's different than the one that you normally look at? You have to recognize this.
There's
Position. What normally goes right here, like off on its own, helium's been moved to right here. And yes, go ahead and put draw helium in right there. That way you know for sure that it's been good. Remember how I said Moseley's periodic table isn't perfect either? Like there's no one perfect periodic table that does everything in perfect order for every type of thing that we're going to be doing. This is one of the exceptions. I moved it over here because of where it falls in which block, okay? So, please be aware of that for this periodic table. All right, so get your first color, whatever color you want to use. I don't care. Any color you want to use. All right, highlighters do work well. You can share them. So, you're going to highlight this first block. So, which block, which sublevel requires the least amount of energy to fill? S. So this is going to be your S block. Do not shade in all of the boxes. Just highlight the outside. All right? Now, to review back from your notes, those of you that are more worried about what I'm telling you than coloring, please listen. In your S block, what's the max amount of electrons? Well, watch this. S1, there's a reason. There's only 2 spots, 2 columns there. That's not a coincidence. All right? Then you have these down the side, 1 through 7. Okay? So S, what's my next level in order? P, right? My P level. Well, your P block is this one right here. Let's either shade the outside or highlight the outside. And then once again, how many total valence, it's not valence, but how many total electrons can the P block have? Well, P1, 2, 3, 4, 5. Not a coincidence that there are 6 columns there. P1, 2, 3, 4, 5, 6 across the top. Then be careful, right? Because if I'm following this is row 1. Is there a P block for row 1? No, it starts at, so 2P, 3, 4, 5, 6, 7. I gave you space there on purpose so you could write. Okay, so next color. What's our next energy level? SP, D, B block, which is here. And how many valence, not valence, I keep saying that. How many total electrons can D block hold? 10, up to 10, right? And once again, not a coincidence. 1, 2, 3, 4, 5, 6, 7, 8, 9, it's not a 9, 10. You can, yeah. I just did it to be quick. Right? Now, this is where you have to be careful. Hopefully nobody's working ahead and thinking they know what to write down. In chemistry, specifically, and a lot of other places, but chemistry, there's exceptions to every rule, right? Like your octet rule, yeah? Like your, there's a bunch of exceptions. Well, there'll be exceptions to almost everything we do this year, okay? So just like you would think that this would be the 4D level, right? It's not. It's 3D. 3D starts in the 4S level. Okay? Just believe me when I tell you that it's all about energy. Okay? So that's 3D, and that makes that 4D, and then 5D, and then 6D. There is no 1 or 2D. There is no 7D. Just do what I do. Okay? We're setting this up so you can use this at home. You will. It's hard to find a good one of these online. Okay? So you want this for you to study from. All right, so there's our D block. And then our last one is our F block. All of this, your actinide and lanthanide series, are your F block. Now, if you notice, how many total electrons can your F block hold? 14, but my paper got cut off. My chart got cut off. If you notice, you're only going to number 12 of them. 7, 8, 9, 10, 11, 12. So what I would do is draw in those extra 13, those extra boxes. You can't. It got cut off when I copied it. Sorry. And then this is your F block. They can't hold up to 14. You need to add the extra blocks. Then these only have, so we need to label the rows. This has a 4F and a 5F. Okay, so I'm going to give you about 1 minute to fill in your atomic symbols for these. You don't need atomic mass. If you want to write the numbers, you can. It's not important, but you are going to want, like I have here, like helium, hydrogen, helium, lithium, beryllium. Go ahead. I would do S block first, and then I would do P block. And then I would do the first 2 rows of D block for sure right now, or as much as you can do. Make sure you get it down right, because you don't want to be studying the wrong thing. You're copying straight from the periodic table. Like, I'll give you a minute to copy straight down, that way you can get them all in there. Or as many as you can. S block, P block, first 2 rows of D block would be the priority in which I write these down. it's up to you if it's an emergency. Go. Yeah, you want to- 'cause this road's not finished. Okay, so enough. Most of you have enough in to at least get started with how we are going to use these. You ready? So you all understand that you can fill these in at any time. I trust that you can copy a periodic table down, okay? What I don't trust is, at least not right now, that you know how to write the electron configuration for sodium down. So you all need to pay attention up here. Stop copying the periodic table. Wherever you are. I know it's super easy. That's why we're not doing it right, okay? So you got enough in, you ready? So, have you all ever played Battleship before? Battleship where you try to hit and sink their ships, right? So if you try to get a hit on, let's say, helium, what grid number would you say to hit helium? 1s2. If you said 1s2, I would say you would hit helium, right? If you wanted to hit neon, what would you say? 2p6. Does that make sense? If you wanted to hit titanium, you would say 3d2. Does that make sense? All right. So with this electron configuration, it's all about where you're going to stop, and those are all stopping points, right? That's one of the biggest things that you got to get. However, to write a full electron configuration, we need to write everything before that as well. Okay, before that as well. So you all watch me do the first one. If I said, what is the full electron configuration for lithium? Right? And I said you have to write everything before. Well, lithium stops at 2s1, right? And I'm going to say this a couple times. When I say read, look at everything before it, you have to read this like a book, like a page in a book. And the good thing is you're going to be reading the same page over and over and over again. It's the same page, the pages don't turn, okay? But when you read in America, you go from top to bottom, left to right. And that sounds very elementary, right? You know that. But that's something you're going to keep remembering, keep in mind, all right? So what do I mean by read like a book? Top to bottom, left to right. So anytime I go to write a configuration, where am I always starting? Right here, top left corner, okay? And so I say, I'm looking for lithium. Is lithium in this first row that I'm reading? Like I'm reading a book, right? I got to read that first line. Is it in that first row? No, so I have to read all the way through it. And so I'm going to put 1s2. By putting 1s2, it shows that I got through that entire row, right? Then I go down to my next row to read. Well, the good thing is lithium falls right here. So what do I write down? 2s1. So this right here, if I get a little closer, 1s2, 2s1 is the full electron configuration for lithium. Let me do a little bit longer one, right? That one was pretty short. Let's do oxygen, right? So if I want to do the full electron configuration for oxygen, where do I always start? Top left. I'm reading the same page I just read before, but instead of stopping at lithium word, I got to go all the way to oxygen, right? So, is oxygen found in my first line of reading? So I got to write down 1s2 to show that I've got through that. Notice how I did not write down 1s1 and then 1s2. That would be too long. I can abbreviate a little bit. If you get through an entire block row, you just write the very last one, right? So, is oxygen found here? So what do I need to write down? 2s2. Now, do I jump down to here yet? I need to finish out reading this row, which is here. Well, now what row am I in? 2p, and the good thing, oxygen stops right here, so what do I write down? 2p4. That is the full electron configuration for oxygen. We'll get there in a second, okay? So now, let's say I want to get to aluminum. All right, watch me do it one more time and then you'll have a few chances, right? Aluminum. So I go 1s2, because I get through. Then I get through my next one, 2s2. Then is aluminum found in 2p. So what do I need to write down? To show that I've gotten through that 2p level. Then I come down here, reading a book, right? Now I got to go down to my third row, my third line. Is aluminum found here? So what do I need to write down? Is 3D a part of this row? So should I write that down? Right? That's like read that, and then reading that. Is that how you learn to read? Oh, I learned to read either, right? So we go all the way over here, and aluminum's found in 3p. That is the full electron configuration for aluminum, right? So before we get to the F, I want you guys to either on the back or on scratch paper somewhere, you can go on the back of your color periodic table. What I want you to do is write down beryllium. Do beryllium. Somewhere. Yeah, write it down. I mean, I'll come around and look. Beryllium, right here, is what? 1s2. Not too terrible, right? Yet. If you understand what we're doing here, when will it start to get terrible? The further you go down, right? Because you always have to read the same page, right? Means you always have to start up here, and if I ask for one way over here, guess what you have to write? Everything before. Now, there's a shortcut that you learn next class, but the shortcut doesn't make sense unless you learn, like you learn long division before mental division, mental math division, right? Because it makes sense. That's what we're doing today. We're getting the base, right? All right. So now let's do calcium. Underneath beryllium, next to wherever you can find spots to do it. Just the ending of it. You need to do everything before it as well. You know what I'm saying? So, remember how we're reading the book? So, calcium is here. Right? So that means what you did is when you went to read this book, you started there. You start reading right here in the middle of the page. You have to start reading. Right? So calcium should have 1s2, 2s2, When you got this, it will no longer be interesting to you. It'll be annoying about how much you have to write. If it's still, none of you have it, like you might have it right now, but I want to see if you have it in 2 days, and that's when I know that you do have it, okay? But if it's still interesting to you, that's good, that's interesting, but you probably don't have it down or memorized until it's annoying to you. That's when you know you have it, okay? So that means you need to keep practicing until you do have it, right? So that's calcium. Now I want to show you something, right? Let's say that we wanted to do, let's see here, scandium. Don't erase that. If I asked you to do SC, which is right here, why am I not having you erase that? If you're reading the same page every single time, and you've already read up to calcium, what can you do? Yes, read the next word, right? So we've got to 4S2, right? What can we just add now? And now you just done scandium. It's no longer, what now? Yeah, there we go. So now what I want you to do, now obviously it's a little bit more difficult for you because you have to write with pencil. I got a whiteboard, I can just erase, right? But if you've already done this, then if I ask you to do, why don't you do arsenic, which is found right here. Go. So what's the incredibly fast way, if this is scandium, what's the incredibly fast way of getting to arsenic? Turn that number to 10, which gets me through this level, right? And then where am I at? 3. Yes? So, something that might be confusing you, especially if you kind of were dozing off or you just blanked out for a second, and that's understandable, is when you look at this, what might be confusing when you look at those numbers? 3 to 4 to 3 to 4? Does that make sense? Like, is that okay? Yes. I'm telling you, like, this is right. Like, this is the right book page that you are reading, okay? If you read the right way, and I hate to tell you don't question it, if you question it, the answer is it's all about energy levels. It's all about available energy, and it takes more energy to be here than it does to be here, but it takes more energy to be in your 4P level than it does to be in your 3D level. It's all about energy, okay? That's my answer to you. So trust that this is the right setup if you follow your rows and reading it the right way, okay? Now, the next thing that I'll tell you is this. If you look at arsenic, what is arsenic's atomic number? Arsenic's atomic number is 33. Y'all agree with that? Which means it has how many protons? And in its ground state, it has how many electrons? They equal each other, correct? and this is no longer scandium, this is arsenic. This is the electron configuration for arsenic. You all agree with that, right? Ready to do some mental math with me? 2 plus 2 plus 6 plus 2 plus 6 plus 2, 20. Right? I told you we're talking about total number of electrons, right? So why am I showing you this? There's two reasons. The first reason is because this is a learning tool. This is not a resource on your test. You all understand that? You will not use this on your test. What you will have to do is use this. Yeah, sure. So you will have to use your periodic table, right? So eventually, by the time we get to October 3rd, you will have to get off of this crutch and only look at this. And actually, not even October 3rd. Your pretest quiz is the 29th. Y'all understand that? So this is a learning tool. At some point, you're going to have to put this down and use that. Y'all understand what I'm saying? Now, I don't trust that any of you can do it right now, but if you do your homework by yourself, if you do the test review by yourself, you will use it so many times that you'll have no choice like your class schedule. You'll just remember it. Everybody got that? Okay? So if you go to page 3, I believe, of your notes, there's a few more examples there. So right now, you and your group, and you can do it separately, then check each other's. There's no cheating, right? You're going to do 1, 2, 4, and 6 are going to be kind of curveballs. And we'll talk about those. You can attempt them if you want, if you know what an ion is, and you should. I taught it to you. We'll review it. But you and your group do 1, 2, 3, and 5, and then we'll talk about our last thing today is 4 and 6. Okay. Go ahead and look up here. I think everybody has at least one done, if not two, where I think like you're getting the hang of it. You ready? Will you all agree with that? And if not, then we'll talk about it, okay? So, this is the part, everything that we've learned up until now, you would have learned in a level class. Everything, they did exactly that same lesson, the exact same stuff, the periodic table, the blocked off, everything. Okay, everything's normal. The only additional thing that we do in this lesson is 4 and 6, right? If I wanted just the fluorine atom, I would have just said fluorine, right? But obviously this ion changes stuff. So an ion, please y'all look up here because this is different, a little bit different. This is the curveball that makes this an honors lesson, okay? An ion is what? An element with a charge. That's great. You're the first class to give me that amount of answer. That's a good thing. An element with a charge. So that's why next to fluorine you see that. Yes? Yes? Now you need to know, where does that -1 come from? Just a little background information. That is fluorine's Lewis dot structure, correct? Yes? Is it happy? What can we do to make it happy? Add one what? It's missing this electron here, right? So to make it happy, right now its overall charge is 0 because it's at its ground state. That's what fluorine normally looks like, right? But it's unhappy. To make it happy, we add one electron. Yes? If we add something negative to an overall neutral element, that's where that -1 comes from. That's why it's there. You all following that? That's a little bit of a review. Okay? So now, let's say the ion wasn't there. What is fluorine's electron configuration? 1s2, 2s2, 2p, 5. Would you all agree with that if you had time to sit down and do that? 2p5? Yes? But now I don't want normal fluorine. I want the ion of fluorine. And fluorine will make a -1. So what did we do again? We added an electron, correct? We added an electron. Remember how we checked to make sure that this was sodium? What did we do? We added all of these numbers up here, right? But now, fluorine does not have, what, 9? Fluorine does not, normally it has 9 electrons down here, right? Total electrons? Yes? But what did we do? So now how many does it have? Does that make sense? Because we made it happy. 2, 4, 9. What's the only available energy level that we can afford to add one to without breaking a rule? Just add one. 2p5 now becomes 2p6 because what did we do? We added an electron. We'll talk about that in a second. Yes. And it'll make sense here in a second. Right? If I do the same thing for number 6 for nitrogen, nitrogen looks like that, correct? The Lewis dot structure, you all look up here. The Lewis dot structure for nitrogen is that. Yes? How does nitrogen going to become happy? It's missing 3 electrons, right? So is it going to add 3 or get rid of 5? Which one's easier? Adding 3. So if I add 3 negative things, its overall charge is going to become what? I add 3 negative things. Negative what? So on your paper, that's why you see a -3 there. Y'all see that? So nitrogen normally has 1s2, 2s2, 2p3. That's nitrogen's electron configuration, right? But nitrogen's ion turns into, what did we do here? Added 3, add 3 to 3, it becomes what? And now we see, what do we notice about these two things? They're the same, but they also look like what? Neon. Look, does that make sense to us? Is neon happy? Is the ion of fluorine happy?
Oh, yes.
Is the ion of nitrogen happy?
Yes.
So if they're all happy, shouldn't they all have a smile on their face and look the same? They all look the same. So that's, yes, that works, because we're talking about ions. Okay? You have one page of homework. It's the very front page. And once you do one of them, they're all kind of in order. They get increasingly bigger. But once you do one, you've already done some of the next. And then once you do that one, you've done some of the next. And really, you're just adding on from what you've done before. It goes actually very quick once you get started. Remember, you have to get off of that periodic table that we built today. At some point, before the 29th.